All right, let's dive in, shall we? Today we're tackling something pretty mind-boggling. Dark matter. You know, that invisible stuff that supposedly makes up a huge chunk of the universe?
Yeah, it's kind of a cosmic paradox, isn't it? We
Okay.
can't see it, it doesn't interact with light, but it's definitely there. We know it because of its gravitational effects.
Right, it's pulling the strings, so to speak, but from the shadows. And get this, some of the smallest galaxies out there, the dwarf galaxies, are helping us figure out a key aspect of this mysterious dark matter, its mass.
They really are. These little guys, often just hanging around bigger galaxies like our own Milky Way, they're turning out to be incredible labs for dark matter research. What we're going to explore today is how exactly these dwarf galaxies are helping us put some boundaries, some limits on how heavy the dark matter particles might be.
So before we get too deep into the dwarf galaxy stuff, let's take a step back for a second. I think it's worth reminding everyone, just what dark matter is at its core.
Absolutely. At the most basic level, dark matter is a hypothetical form of matter. And the key word here is hypothetical. It doesn't interact with the electromagnetic force.
Mm.
That's why we can't see it. No light, no radio waves, no X-rays, nothing. Everything we know about it comes from how it interacts gravitationally with the stuff we can see.
So it's like a ghost, leaving its fingerprints all over the universe but never showing its face. What's the evidence, though, the really concrete stuff that makes us so sure dark matter is out there?
Well, the evidence is not just one thing. It comes from lots of different places and scales in the universe. One of the most convincing early clues came from studying the way galaxies rotate, what we call galaxy rotation curves. Back in the 1970s, astronomers like Vera Rubin, they were looking at how stars and spiral galaxies move. And they found something odd. The stars in the outer parts of these galaxies were moving way faster than they should have been based on the amount of visible stuff, stars, gas, dust that we could see.
So there had to be more mass lurking around somewhere to hold these speedy stars in their orbits.
Exactly. And that's where dark matter comes in. It's like this invisible halo surrounding these galaxies, extending way beyond the visible part. And its gravity is what keeps those outer stars from flying off into space.
Makes sense. So it's kind of like we're seeing the effects of this hidden mass, this dark matter, through how it affects the visible stuff.
Right. And we see similar effects when we look at the motions of galaxies with galaxy clusters, groups of galaxies bound together by gravity. The speeds we observe are often much higher than what we'd expect if only the visible matter was contributing to the gravitational pull. Again, pointing to a lot of extra mass that we can't see.
Now, there's also gravitational lensing, right? That one's always fascinated me. It sounds so sci-fi.
It's pretty amazing. Gravitational lensing happens because massive objects, anything with a lot of gravity, can actually bend the path of light. So when light from a distant object passes by a really massive thing, like a galaxy cluster, its path gets distorted, bent. And the amount of bending tells us about how much mass is there.
So it's like the light is giving us a sneak peek at this invisible mass, acting like a tracer.
Exactly. And the amount of lensing we see around galaxy clusters, it tells us there's a lot more mass there than we can account for just by looking at the galaxies and the hot gas we can see. It's like there's this huge, invisible, weight-warping space-time around these clusters.
Okay, so we've got galaxy rotation, galaxy clusters, and gravitational lensing all pointing to dark matter. Anything else?
Oh yeah, there's more. One really cool piece of evidence comes from something called the bullet cluster. It's actually two galaxy clusters that collided with each other. Now, when they smashed together, the hot gas in each cluster, it interacted and kind of slowed down, forming this big cloud in the middle. But when we looked at the bullet cluster with gravitational lensing, we saw that most of the mass, presumably the dark matter, didn't interact much at all. It just passed right through the collision, kind of like a ghost.
So it was like watching two massive things collide and seeing that the bulk of their mass didn't even flinch.
Pretty much. And this tells us that dark matter, whatever it is, doesn't interact with normal matter, or even itself, in the same way that ordinary matter does. Then we have the cosmic microwave background radiation. It's the afterglow of the Big Bang, and it gives us a snapshot of the universe when it was extremely young. And the patterns we see in this radiation, they fit best with a universe that has a lot of dark matter in it.
Wow. So we've got evidence from the way galaxies rotate, from galaxy clusters, from gravitational lensing, from colliding galaxy clusters, and even from the earliest light in the universe. I'm starting to get the picture, but hold on a sec. Haven't there been alternative theories out there? Ideas that try to explain all these things without dark matter?
There have been, yes. Some scientists have proposed modifications to our understanding of gravity, especially on really large scales.
Right.
One idea is called modified Newtonian dynamics, or MOND for short. It basically suggests that gravity might behave differently than we think in areas where the gravitational pull is very weak, like in the outer parts of galaxies.
So they're saying that maybe we don't need dark matter. Maybe it's just that gravity works differently than we thought.
Right. But the problem is, these modified gravity theories, they haven't really been able to explain all the observations that point to dark matter. So while it's good to keep exploring different ideas, most scientists still agree that some kind of dark matter is the most likely explanation for what we see in the universe.
Okay, so dark matter is still the leading contender. Now let's finally get to those dwarf galaxies you mentioned earlier. What makes them so special for studying dark matter?
Well, dwarf galaxies, especially the ones called ultra-faint dwarf galaxies, or UFDs, are just chock full of dark matter. We're talking like 99.9% or even more of their total mass is made up of dark matter. They're basically giant clumps of dark matter with just a smattering of stars here and there.
So they're almost like pure dark matter laboratories.
Pretty much. And because they're so dominated by dark matter, it makes it much easier to study its effects. It's like having a really strong signal, you know? Plus, we think these UFDs are some of the oldest galaxies out there, probably formed really early in the universe.
So it's like looking back in time to the early universe and seeing dark matter in action.
Exactly. Now, to really understand how these dwarf galaxies are helping us figure out the mass of dark matter, we need to talk about something called the de Broglie wavelength. It's a concept from quantum mechanics, the physics of the very small.
Quantum mechanics. Now things are getting really interesting. How does that tie into the mass of dark matter?
Well, one of the leading ideas is that dark matter might be made up of these super-light particles called bosons. Now, bosons, they can act like waves as well as particles, kind of weird quantum thing. And every particle has this associated wave called the de Broglie wavelength. The lighter the particle, the longer its wavelength, the more spread out it is.
So are you saying that if dark matter is made of these light bosons, it might act like a wave on a galactic scale?
Yes, exactly. And there was this early idea that if the de Broglie wavelength of these dark matter particles was bigger than the size of a dwarf galaxy, it might prevent these galaxies from forming in the first place. You see, the wave-like nature of dark matter, it might smooth out the clumps of matter that galaxies need to form.
Ah, I see. So the very existence of dwarf galaxies might tell us that dark matter can't be too light, otherwise it would be too spread out to let these galaxies clump together.
That was the thinking, yeah. But it was a bit of a simplified argument. Recent research has taken a much more rigorous approach to nail down a more precise limit on the mass.
Okay, so tell me about this new research. What did they do differently?
Well, they focused on one specific dwarf galaxy called Leo II. It's one of the many dwarfs orbiting our Milky Way. And they used very precise measurements of the speeds of stars within Leo II. You see, because dwarf galaxies are so dominated by dark matter, the way those stars move is basically telling us about the gravity of the dark matter.
So they're using the stars as tracers, just like with gravitational lensing, but on a smaller scale.
Exactly. And what's really cool is they tried to map out the dark matter in Leo II without making too many assumptions about what kind of dark matter it is or how it behaves. They wanted to let the data speak for itself.
This is a really data-driven approach. I like that. So what did they find?
Well, they said, okay, let's imagine that dark matter is made of these light bosons with a noticeable de Broglie wavelength. Now, these wave-like particles, they would create this kind of fuzzy core in the center of the galaxy. They then compared this fuzzy dark matter model to the actual distribution of dark matter they inferred from the star's movements.
So they were trying to see if this fuzzy, wave-like dark matter model matched up with what the stars were telling them.
Right, and they kept tweaking the mass of the hypothetical dark matter particle, which changes how fuzzy it is to see if they could get a good match.
Did they?
Well, they found that if the dark matter particle was too light, the fuzzy model just didn't fit the data. The dark matter distribution from the stars was too different from the fuzzy model.
So they hit a point where the wave-like nature of dark matter just didn't jive with what they were seeing in the galaxy.
Precisely. And that point gave them a new lower limit on the mass of the dark matter particle.
Okay, drumroll please. What's the new lower limit?
They found that the dark matter particle has to be heavier than 2.2 times 10 to the minus 21 electron volts. That might sound like a tiny number, but it's actually significantly heavier than the old estimates.
So heavier than we thought. What does that mean for our overall understanding of dark matter?
Well, it's a big clue. It helps us narrow down the possibilities. Some of the really light dark matter candidates, like certain types of axions, they might be out of the running now.
So by studying these dwarf galaxies, we're not just learning about dark matter, we're actually helping to rule out certain ideas about what dark matter could be.
Exactly. It's like a process of elimination, getting us closer to the truth. And this new mass limit also impacts how we design experiments to actually detect dark matter particles here on Earth. If we know they have to be heavier than we thought, we might need to adjust our experimental setups to be more sensitive to those heavier masses.
That's amazing. It's like these tiny, faint galaxies are guiding our search for something we can't even see.
They really are. They're like cosmic beacons, shedding light on one of the biggest mysteries in physics.
All right, so as we wrap up this deep dive, what's the big takeaway message for our listeners?
I think the main point is that dwarf galaxies are turning out to be incredibly valuable tools for understanding dark matter. By carefully studying the motions of stars in these galaxies, we can probe the fundamental properties of dark matter, like its mass. And in this case, we've learned that dark matter particles have to be heavier than we previously thought.
It's a great reminder that sometimes the biggest discoveries come from the smallest, most unexpected places.
Absolutely. And it's important to keep in mind that we've only scratched the surface. There's still so much we don't know about dark matter. This new research is a step forward, but it's based on the assumption that dark matter is made of just one type of particle. It could be much more complicated than that.
Right, there could be a whole zoo of dark matter particles out there.
Exactly. So the mystery continues.
Well, I think we've given our listeners plenty to ponder. For those who want to explore further, I definitely recommend looking into the concepts of dark matter, dwarf galaxies, and the de Broglie wavelength. It's a fascinating journey into the unknown.
Indeed. And remember, the universe is full of surprises. Keep exploring, keep questioning, and who knows what you might discover.
Great advice. Thanks for joining us on this deep dive. Until next time, keep looking up.